approximations. So out of the three distributions you have, binomial, Poisson, and normal. The idea here is the normal is your, well, it's where it's easiest uh, to manage even larger values. So you can go from binomial to Poisson. You can go from Poisson to normal. You can also go from binomial to normal, but you won't be going from normal backwards or anything. It's either binomial to Poisson, or binomial to normal, or Poisson to normal. These are the three distributions that you could be doing. So if you want to go from binomial, uh, let's say you have a distribution that is binomial, so you have n and p, and you want to go to Poisson where you will have lambda. Again, lambda is mean, so the conditions for this is that n has to be greater than 50, so it's large enough, uh, and np has to be less than 5. So like both these conditions need to be fulfilled for you in order for you to approximate. And the idea here is that since lambda is basically your mean, and mean, as you should know, and as I think it's even given in your MF9 table, is the product of number and the probability. You do so, you get Poisson. Very simple. If you want to go from binomial, excuse the handwriting, to let's say normal, right? Well, the conditions for this, now this is slightly important. So for this one, NP has to be less than 5 and NQ has to be less than 5. So don't mix these two conditions up. There were questions which some people were getting confused in. They were converting directly from binomial to normal, even though this second condition was not fulfilled. What they should have been doing is converting into Poisson, because they had a very high n and a very small p, but a very large q. So just be a little wary of your conditions. And what will happen here is that, and this is should be, I'm not too sure, I think it's given in the MF9 table as well. Mean again is NP, your variance, which is sigma square, standard deviation square is NP, 1 minus P, which is basically what some people did just denote as Q, which is the probability of the event not happening. So obviously just subtract by 1. And that should give you your normal distribution. With X, however, you do have to apply what is known as a continuity correction, because you are going from a discrete distribution to a continuous distribution. And I'll upload a separate video about continuity corrections, perhaps a little while later. The other one you could be going from is, so Poisson, where you have your lambda, you could be approximating to normal, where you have this and sigma square. Now, mean would obviously still remain lambda because, well, lambda is mean. And your variance also remains lambda, which means that if you want to find out your standard deviation, that is root lambda. But yeah, so if you do, what basically it then looks like when you do approximate is somewhat like this: mean is lambda and variance is also lambda. The idea here is if lambda is basically large, if it's large enough, I think it's greater than 15. So if it's greater than 15, you can assume that it would be similar enough to result in a somewhat of a bell-shaped curve, so a normal distribution. Again, the greater the lambda, the better, or the more accurate, the more accurate the distribution, because that is when not more accurate the distribution, more accurate the approximation, because with greater values of lambda, that is when it properly looks like a bell-shaped curve, and you can and then it just assimilates your normal distribution even more when lambda is high. when it's great. But the condition here is greater than 15. And again, because you're going from a discrete to a normal distribution, you have to apply a continuity correction, which I'll explain in a different video. But this was it for approximations.